In this discussion video, we will do some logarithmic differentiation practice problems. So I want to first review some of our log rules. And each of these log rules, I'm going to assume that all of our logs are defined. We need them to all be defined to be able to apply any of these. So the first log rule says that when I have a power like this inside of my log, we can bring that power to the front and get p times log base b of a. And the second log rule says, well, when we add two logs like this with the same base, that becomes one log, and then you multiply the insides, log base b of x times y. And when you subtract two logs with the same base, it also becomes one log, but you divide the inside. So you do the first inside divided by the second inside. Okay, so we introduced this technique called logarithmic differentiation in class. And this will help take derivatives of powers, products, so things multiplied, and quotients. Powers, products, and quotients. Quotients are when things are being divided. Okay, all of these are things that simplify really nicely when they're inside of a log. So logarithmic differentiation will involve taking a log of both sides of an equation and then taking a derivative. All right, so I want to do worksheet 7, problem 6c. First, I want to compute the derivative of the function y equals x to the power x. So pause it and try this for 4 minutes. 4, 3, 2, 1, 4 minutes to try this. All right, so the first thing that I want to mention about this is, we mentioned this in lecture as well, but to do this derivative, I can't just use the power rule that says derivative of x to the n is n x to the n minus 1. I can't use that because to use that, my exponent has to be a constant. And here, my exponent's a variable. All right, so I can't use this. I also can't use, we have one other derivative rule for exponential things. And that's derivative of a to the x. Derivative of a to the x is ln of a times a to the x. I can't use that because in this rule, the base of the exponent needs to be a constant. And the base of my exponent is x, and that's a variable. So we can't use this either. All right, so what we'll try to do is we will take the ln of both sides and use log rules to simplify. Use log rules to simplify. All right, so doing this, we will get ln of y equals ln of x to the power x. On the right-hand side, I can bring this power to the front to get x times ln of x, and that's going to be equal to ln of y. Now I'm going to differentiate implicitly. So differentiate implicitly. Okay, so we will take the derivative of both sides. We'll take d dx of the left-hand side and d dx of the right-hand side. So d dx of ln of y and d dx of x, ln of x. On the left-hand side, when I do this derivative, I do chain rule, and I'll get 1 over the stuff, 1 over y, times the derivative of this stuff, dy dx. On the right-hand side, the variables in the function and down here are the same. So this is a normal derivative. And I do product rule. I'll get x times the derivative of the second thing, 1 over x, plus the second thing, ln of x, times the derivative of the first. Derivative of x is 1. All right, so now to isolate dy dx, I will multiply both sides by y to get y times this whole thing. I could cancel the x's to get 1, and then plus ln of x. And the last step is, my original function was purely in terms of x. And right now I have a y in my derivative. So let's substitute in for what y equaled. Y was equal to x to the x. So I get x to the x times 1 plus ln of x. And that is the derivative of x to the x power. All right, so notice, the tip-off that logarithmic differentiation was going to be helpful was, I have a power here I have this x in the exponent, and it wasn't just something I could use one of my previous rules on. So specifically, I had variables in the base and in the exponent, and that's commonly something that we'll use logarithmic differentiation on. All right, let's do another example. Okay, so now I want to compute the derivative of this function here. Okay, so I got this fraction, I got things being multiplied on the top, a bunch of powers and roots. Okay, so method one is, I could definitely do this directly using rules I already have. So if we were to do this directly, we would use quotient rule first. We would use quotient rule, and then after that, we would be using chain rule and product rule. We use chain plus product rules. But it would definitely be pretty tedious to have to do that. All right, so this would be tedious. So I'll put a sad face. All right, so we'd like a better way. And this is where logarithmic differentiation is going to come in. So method two is we could use logarithmic, I'm just going to put a period, apostrophe, sorry, abbreviate, logarithmic differentiation. Okay, so I'm going to take ln of both sides, ln of y, and ln of the other side, ln of this whole thing, x to the fourth plus 1 being cubed times sine to the sixth of x over that fifth root of 1 minus 3x. Because the nice thing about the right-hand side is I have a product of two things on the top, and that's all divided by something, and there's a bunch of powers. So I'm going to get to use a bunch of log rules on the right. I will get ln of this x to the fourth plus 1 being cubed added to the ln of that sine to the sixth of x. And then because that whole thing is being divided by this fifth root, I'm going to get minus, ln of 1 minus 3x. And it's going to be helpful to rewrite the fifth root as a 1 over 5 power. Okay, so ln of y equals this. So I can continue to simplify. Ln of y equals all these powers I can bring to the front. Okay, because the 3 is the power of everything else that's inside. I get to do 3 times ln of x to the 4 plus 1. Even the sixth power I get to bring to the front. Because remember, when I write sine to the sixth like this, that means sine of x, that quantity being raised to the sixth power. That's what this notation means. That's just how we write exponents on trig functions. So I can bring the 6 in front and get 6 times ln of sine of x, and I can bring the 1/5 in front and get minus 1/5 ln of 1 minus 3x. And now this derivative is a whole lot easier to do. I'm going to take ddx of both sides. On the left, I'll do chain rule. I'll get 1 over the inside, 1 over y, times the derivative of y, which is dy dx. On the right, well, I'll get 3 times the derivative of this ln term. That's also going to be chain rule. I'll get 1 over the stuff, 1 over x to the 4 plus 1, times the derivative of the stuff, which is 4x cubed. For the next ln, the 6 will stay there. I'll get 6 times 1 over the stuff, 1 over sine x, times the derivative of that inside, which is cosine x. Okay, so this is a lot nicer than having to do all of that quotient, product, chain rule that we were seeing more before in method 1. Okay, and then I get minus 1 over 5, and then times, I'll get 1 over this stuff, 1 over 1 minus 3x. Times the derivative of this inside, which is negative 3. All right. So to end this, I'm going to multiply both sides by y. I'll get dy dx and do a little simplification. So when I multiply by y, I'll get y times all of this stuff. And as we saw before, let's just plug back in for what the y was, because I'll need to get it all in terms of x. So if I plug back in for that y, I will get, let's see, what was it? It was like x to the fourth plus 1, that being cubed, times sine to the sixth of x over that fifth root of 1 minus 3x. This whole thing is y. And that's going to multiply all of this other stuff, which I'll simplify. So 3 times 4x to the third, that's 12x to the third, over x to the 4 plus 1. Then I'll get plus 6 cotangent x. That's cosine over sine. And then I'll get plus 3 over 5, and then times 1 minus 3x. Okay, I've just copied that at the top of the page to give myself more room. And that is our answer.